Hi everyone, welcome to lecture number 16 for Physics 151. The main topic for today is circular motion. So we're going to start off our theory with a review of period and frequency and angular frequency. Then we'll get into the kinematics and dynamics of uniform circular motion. I'm going to omit examples of circular motion in a vertical circle, where the weight of the object varies in direction relative to the circle and makes things more complicated. So we'll stick with the simpler examples of motion in a horizontal circle or motion where the weight of the object is just negligible or unimportant. The example I'll be doing at the end of the lecture is from tutorial 16, and there are some more examples there for you to try. And then the circular motion problems in our online homework are located in the first portion of this single assignment, online homework 16 through 18. So this lecture is going to start off with about 6 or 7 theory slides. We're going to collect a whole bunch of equations, and then we'll put them all to use at the very end with example problem from the tutorial. Let's start off with a definition of period and frequency, which is something that many of you are probably already familiar with. The period of any repetitive or periodic motion, as we like to call it, is the amount of time it takes for that motion or that system to complete exactly one cycle or one of these repetitive events, whatever it might be. So that could be for a pendulum, the amount of time it takes to complete one full back and forth swing. For a record, it could be the amount of time for one rotation, for planet, one orbit, and so on. Or for waves, the amount of time it takes from one crest to pass you until the next crest passes you. Because this is just a time, the dimensions are, of course, time, and the MKS units are seconds. In the back of your mind, though, remember that this is the time per one cycle or the time per one revolution, although we usually don't write that in the units. And bear in mind that that cycle and revolution are dimensionless quantities. So even if we did write it down, we can simply eliminate them without having to cancel them out. We can just cross them out or make them vanish because they have no dimensions of their own. Frequency is the number of cycles that are completed of this repetitive or periodic motion per unit of time. So this unit of time could be a second or a minute or an hour. It could be anything. And if we count up the number of cycles of the orbits or the pendulum or the sort of record player rotations during the unit of time that we choose, then we get the frequency. By the way, this doesn't have to be an integer number. This could be a fractional number or decimal number of cycles. So therefore, the units of this are the number of cycles per unit of time or the number of revolutions per unit of time. But cycles and revolutions are dimensionless. So that means it's basically just inverse time or 1 over time. It's a reciprocal of time. So 1 over seconds, specifically cycles per second or revolutions per second, is called a hertz, capital H, lowercase z. So make sure that you keep your capital and lowercase correct. So that's the MKS unit, of course, using seconds. Oh, and it's also the CGS unit. It is both. So if you look at the definition here, period is the amount of time per one cycle, and then frequency is the number of fractional cycles that are completed per time. These two are simply reciprocals of each other. And indeed, that's what we have in these equations down here at the bottom. Regular frequency is equal to 1 over the period, and period is equal to 1 over the regular frequency. So I recommend these equations show up over and over again in physics. They're used with rotation, they're used with waves, and they're used in Physics 152. So I recommend that you memorize the unit hertz and that you memorize these expressions right here. So let's add one more quantity, which is similar to regular frequency here, but it's angular frequency. And instead of defining, and angular frequency is defined just a little differently. Instead of being the number of cycles per unit of time, it's a number of sort of radians. We could have used degrees, but radians have the advantage of being dimensionless because of the way they're defined in trigonometry. So in other words, radians are a distance divided by a distance. So this is a sort of way of, again, talking about the amount of rotation that an object has undergone. If this is, suppose that the periodic motion we're talking about is a spinning of an object or an orbiting of an object, then it's easy to think of this as the sort of amount of rotation that that object undergoes per second or per minute or per whatever unit of time. So the angular unit we're going to use is the radian. So the dimensions are going to be radians per time in MKS units. That'll be radians per second. However, like I said, radians are dimensionless. So mathematically, this looks the same dimensionally as simply 1 over seconds. Radians per second and 1 over seconds mathematically look the same. But the actual quantities of angular frequency and regular frequency differ by a factor of 2 pi, because there are 2 pi radians in one cycle or one revolution. So if we know regular frequency, we can get angular frequency by simply multiplying by 2 pi. This 2 pi is basically converting cycles per second into radians per second. Because this is the definition of angular frequency compared to regular frequency, and because we know regular frequency is 1 over period, we could rewrite this first expression in terms of period and get the second expression. I recommend that you memorize that one cycle is 2 pi radians, and that you just sort of memorize that omega is equal to 2 pi times f. Those are expressions that you'll probably use a lot in the future when omega shows up again in other contexts. Oh, one more thing I wanted to mention, two more things. Angular frequency is sometimes called angular speed and angular velocity when we're talking about an actual spinning object, and that's used in rotation. But when you're talking about something like a wave or a pendulum, where it's not actually physically rotating, then people will always use the term angular frequency. Also, on the previous slide, I forgot to mention that RPMs, revolutions per minute, are a regular frequency, because regular frequencies involve cycles or revolutions per unit of time, as opposed to an angular fraction of that, like radians. So revs per minute is a way of talking about frequency. However, notice that it's not an MKS unit of frequency, it's not a hertz, because the minute is not the MKS unit of time. So to get hertz, you would take RPMs and you would divide by 60 to turn it into revolutions per second. All right, now let's put those definitions to work for period, frequency, and angular frequency, and talk about uniform circular motion. So let's define what we mean by uniform and circular. So uniform, in this context, uniform means that the speed of the object is constant. And then circular, as we all know, means that the radius of curvature of the path of the object is constant over time, okay? So in other words, the object's tracing out a perfect circle, and the radius of that circle will be capital R, although you can use lowercase r, and that's fine as well, which I accidentally did right here. And the uniform part here means that the speed with which the object traces out the path through space is going to be constant. Well, remember the definition of speed? The definition of speed was distance traveled along the path length divided by the time it takes to travel that distance. So we know that a circle, an object that is tracing out the same circle over and over, is going to trace out one circumference of that circle in one period of time. So that's what we have here. This is one circumference of the circle, 2 pi times r, divided by the period, capital T. So therefore, this must be the speed of an object that's tracing out uniform, or that's executing uniform circular motion. Because we know that 2 pi over t is also omega, then we could replace that by just the angular frequency or angular speed, and we have the same expression, except it's written here in terms of omega. Most of the time, you're probably going to use the first expression for uniform circular motion. However, the second expression shows up a lot more in things like rotation problems. Now, this is the speed, which is the magnitude of the velocity, as you know. But what about the direction of the velocity? Well, in chapter 3, when we were talking about two-dimensional kinematics, we learned that the direction of an object's velocity is always tangent to the object's path. So the velocity vector of an object at any moment in time is tangent to the path. Here, the path is a perfect circle, so that means that for an object in uniform circular motion, the velocity vector will always be tangent to the circle at all moments in time. We'll see that on a diagram coming up. So, just to summarize, the magnitude of the velocity vector is given by this speed up here, and it remains constant at all times. That's the uniform part of uniform circular motion. Whereas the direction remains always tangent to the circle, which means that the direction of the velocity will keep changing during as the object executes one trip around the circle. The direction of the velocity will keep turning and turning and turning that entire time. So the direction of the velocity is not constant. Right? The speed is constant, the magnitude of the velocity is constant, but the direction is not. So that's the basic sort of velocity and speed part. Now let's think about acceleration. Initially, you might think, well, the speed is constant. So does the object have any acceleration? Well, it turns out the answer is yes, it does. And the reason is not because the magnitude of the velocity is changing over time. In other words, the object is not speeding up or slowing down, but the object is turning. And any change to the velocity vector at all requires an acceleration, or is an acceleration. It's defined as an acceleration. And that includes the direction of the velocity vector. So it turns out if you look at what the velocity is doing at 2 adjacent moments in time, you can see that between this moment here and that moment there, the velocity is turning, right? It was pointing to the upper left, and now it's pointed just to the left. So the change here is sort of a downward change. So that would be sort of toward the center of the circle. And if we compare the next 2 moments in time, it's the same thing. The change in the velocity vector is sort of to the lower right, which is, again, toward the center of the circle. It can be shown that, in fact, the direction of this acceleration instantaneously between 2 very close together moments of time points exactly toward the center of the circle for uniform circular motion. And it keeps on pointing toward the center of the circle at all times. So we're going to call this acceleration of the object that's tracing out this circular motion the centripetal acceleration, or also the radial acceleration. Our book uses the rad subscript. Other books use just a C or a CP for centripetal, and it's the same thing. So this acceleration vector will always point toward the center of the circle, right, or toward whatever the axis is of the revolution of the object that's tracing out a circle. So in other words, the direction of the acceleration keeps changing continuously over time, right? It's pointed always toward the same axis or point, but the actual physical direction. Here the acceleration points up, here it points to the left, there it points down, there it points to the right. The magnitude of the acceleration is constant. And I'm not going to derive it here, but you can look at our textbook if you'd like a derivation, and it can be shown that the magnitude of this acceleration is equal to v squared over r. So v is that speed, which has a constant value all the way around, and r is the radius, which is also constant the whole way around. So therefore, the acceleration is constant. Notice that we know that v is also equal to omega times r. So if we plug in omega r into v for the numerator, this expression can also be written as omega squared times r. I'm sorry, that's a typo. It should be omega squared times r. Again, our textbook shows the first expression, not the second, but there are times when the second one can be useful as well. So just to be clear, this should be omega squared times r. I'll correct that on the slides that I have uploaded. All right, so just to summarize here in this gold box, this again is a little repeat of what's been on this slide and the previous slide. The velocity vector is always tangent to the circle, and it always has the same constant magnitude, but the direction keeps changing. The acceleration vector always points toward the center of the circle. It also has its own same constant magnitude, but its direction keeps changing as well. So I recommend that you memorize this. For an object tracing out circular motion, the velocity is always tangent to the circle, and its acceleration is always toward the center of the circle. Now, finally, the last bit of theory to talk about is force. If an object is constantly accelerating, like it is here, if it's always undergoing an acceleration, doesn't that require some net force to create that acceleration, according to Newton's second law? And the answer is yes. In fact, it does require a net force. So an object can only trace out uniform circular motion if there is some net force acting on it at all times toward the center of the circle, the center of the revolution that it's undergoing. Now, I'll get to that in just a moment. I want to mention one quick more thing about acceleration, and this is from section 3.4. If you don't have uniform circular motion, meaning if you have motion along a circle, but the object is speeding up or slowing down, so the speed doesn't stay uniform, then for an object to speed up, then instantaneously, you must have a forward acceleration. But for an object to trace out a circle, you need to have an inward acceleration toward the center of curvature. So that means the total acceleration of the object, here is a top view of a car, the total acceleration is going to be equal to the vector sum of the inward acceleration, which is our centripetal acceleration, and some forward acceleration. So you're going to end up having a net or total acceleration that is not exactly toward the center of the circle. And the same thing would be true if the object were slowing down. Then it would have a backward acceleration plus an inward acceleration because of the circular motion, the curve here of the circular path. And then the net acceleration will be, again, not toward the center of the circle. The only time the acceleration is exactly toward the center of the circle is if the speed of the object along the path is neither speeding up nor slowing down. Then there's no tangential acceleration at all, like there is in these previous two examples. These are the tangential components of acceleration, and all we have is the radial component of acceleration, and that's it. Okay, so this is the situation for uniform circular motion, which is what we already know. I just wanted to point out that if you speed up or slow down the object, then there's a component of acceleration that leads the center of the circle or lags the center of the circle. All right, so now on to that force that we postponed for one slide. So yes, as long as an object is always accelerating, in this case toward the center of the circle, then there must always be a net force acting on the object in the same direction. So in this case, it's also toward the center of the circle. So in our textbook, that is called net radial force, radial meaning along the radius. Now, the radial could be away from the center of the circle, but in this case, if the object is undergoing uniform circular motion, then we know that it has to be toward the center of the circle. So the term radial alone can mean outward or inward. But in this case, we know the net force has to be inward if the object is successfully executing circular motion. So we know that the acceleration, we know that the direction of the acceleration is always toward the center. So therefore, the direction of the net force always has to be toward the center to match. We know that the magnitude of the acceleration is constant, so therefore the magnitude of the net force must also be constant and just equal to the object's mass times that constant acceleration. So here is that constant acceleration, again over here. And unfortunately, again, there's a typo, omega squared times r. Now, just a quick note here, right? What are the physical forces that are causing this this net radial force? Well, it could be a single force, like in this case here. This is the mass that's executing circular motion around the athlete. Here, it's the tension in this steel cable. So the tension is always acting toward the axis of rotation, which is close to the athlete. So that's it. All it takes is the one force. If we ignore the weight of this ball, if we just ignore the Earth, and imagine this athlete were doing this swinging out in outer space, then the only force that's needed to act on this big metal ball is just the tension in the cable. Or if you think about the Earth orbiting the sun, there's only pretty much a single force on the Earth that's doing that. So that is the force of gravitational attraction. So the sun pulls on the Earth, and that is the force, that is the radial force, and that's all that's necessary. It is possible for this radial force here to be the sum of two or more components, radial components of multiple physical forces. So this could actually be the sum of a component of normal force plus a component of friction plus a component of something else. But it doesn't have to be. It could be just a single force. It could be just a component of one force only. And that's the example. That's what the situation that we're going to mostly use in this class, just to sort of simpler examples where it's just the tension and we don't worry about anything else. Now, also a quick vocabulary clarifier. When you see the word centripetal, right, which I will once in a while mispronounce it on purpose as centripetal, just to really distinguish it from centrifugal. But centripetal is the way it's usually pronounced. The pedal part means pushing toward. So centripetal means pushing toward the center. So centripetal acceleration is toward the center of the circle. Centripetal force is a nickname that's sometimes used for this net radial force that is toward the center of the circle as well. The term centrifugal, fugue means flight or flee, and so centrifugal means fleeing away from the center, right? Fleeing the center. Notice that none of the quantities, physical quantities we've discussed so far, are actually centrifugal. None of the acceleration does not point away from the center, the acceleration of the object, right? And the force, net force on the object does not point away from the center. Instead, they both point toward the center. So the actual physical quantities are centripetal acceleration and centripetal force, but not centrifugal. I'll say more about that on the next slide. Finally, one last clarifier. Our textbook is pretty careful to avoid the term centripetal force. But if you look at older books or other books, then you'll find that that term does show up. But I want to clarify what it is. And it is just a nickname given to this net radial force, which is provided by real life physical forces like tension or normal force or gravity, like I was talking about a moment ago. These are physical forces that have a component in the radial direction. And when you add up all those radial components, you get a sum. And sometimes that sum, that radial sum of forces is nicknamed centripetal force. However, there is no other physical force called the centripetal force. The centripetal force is not a thing. It is a total of radial components of other actual forces whose names we know. So that's, anyway, that's what that means. It just reminds us the direction that sum points, which is toward the center. So one last sort of comment about applications, and that is, and this is building on that centrifugal term. So if you have an object that is executing uniform circular motion, and it is pressed against a wall or a surface while it's doing that. So if you imagine, for example, in the centrifuge, the liquid inside these vials is pressed against the bottom. So that's sort of the wall, if you will, that is pushing inward on the liquid to keep that liquid moving in circular motion. Or in the case of clothes that are in a spinning washing machine during the spin cycle, it's the outer wall of the drum that presses inward on the clothes. And so it's that normal force from the wall of the drum that that is providing an inward centripetal force. Then, from the point of view of the liquid in the vial or the piece of clothing pressed against the wall, that piece of clothing thinks that it is experiencing an outward force. And if you have ever been in a car that undergoes a tight, rapid turn, you feel like there's some sort of a force pushing on you away from the center of curvature of that turn. Now, this is simply an illusion. This is an apparent force, an apparent acceleration away from the center of the circle. And it's simply due to your body's own inertia. Your body's own inertia. So, for example, if we think about a chunk of clothing that's spinning around and around, at any moment in time, that chunk of clothing's velocity is tangent to the circle. So if there were no force, no net force acting on that chunk of clothing, it would travel off in a straight line. But instead, the wall comes around to meet it and keeps pushing that chunk of clothing toward the center. So from the clothing's viewpoint, from the clothing's reference frame, the clothing thinks it's being pressed against the wall, when in fact, in real life, in the sort of reference frame of the washing machine, it is the wall that is pushing against the clothing at all times. But from the clothing's point of view, it has this apparent sort of outward force that is pressing it against the wall. So this isn't a real force, this is a fictitious force. The actual force is inward that's acting on the clothing. But it does have the advantage of making the clothing think that it's being pressed against the wall by some sort of really strong force. So when it's a person being pressed against a surface, we might call this an apparent gravity or an artificial gravity. So if you imagine that the space station is spinning with some moderately fast speed, people could then walk around. People would then be pressed against the inner edge or inner wall of the space station, and they would then be able to walk around. And the faster the space station spins, the stronger that apparent gravity would appear to be. So that can be really useful. In fact, that's probably at the present time, the only technology we know of to create a sense of artificial gravity for any long-term space travel. This is also used to squeeze the liquid out of your wet clothes by making them think that they're under many tens of G's of gravity. And so it just wrings the water out, and the water drains through these tiny perforations, these small perforations in the wall of the washing machine. There's something for salad that will drain your lettuce that's called a salad spinner, and it's a little centrifuge and it does the same thing. And for blood vials, the point of the centrifuge is to help separate the different densities of stuff in the blood. So the cells will sink to the bottom and the plasma will float to the top. So centrifuges just accelerate that separation process, which might happen if you just stood the vial on the counter, but it would be a lot slower. All right, so just bear that in mind. If you're ever asked to calculate what the apparent gravity is that an object feels when it's undergoing uniform circular motion, all you need to do is just calculate what the centripetal acceleration of the object is, and that's equal to the illusion of the apparent gravity that the object thinks it feels. Those two have the exact same strength. The only difference is their direction. The object thinks it feels an apparent gravity outward from the center of the circle, in other words, centrifugally, but the real life acceleration of the object is actually inward toward the center of the circle, centripetally. The apparent weight that the object seems to feel is the same thing. It's equal in strength to the net radial force acting on the object inward, but the object, in the object's frame of reference, it thinks that that apparent weight is outward. All right, let's do an example now. So I'm going to solve the multi-part problem, problem number 2 on tutorial 16, which just asks a bunch of questions about a top-loading washing machine and when it's on the spin cycle. So here's tutorial 16, and I'm going to leave problem number 1, which is similar to problem 2, as an exercise for you. This is just involving a point on a record player as that record player turns round and around. And then near the end, a little coin is resting at that point. All right, so please try that one later. It'll use a lot of the same equations that we're going to use right now for problem 2. So suppose that you have a washing machine, and during its spin cycle, it rotates at an angular speed of, so this is an angular frequency, right? Sometimes that term angular speed or angular velocity is used as a synonym. An angular speed of 60 radians per second. Okay, and that's 2 significant figures because of that little period right there. And suppose that the radius of the drum, the inner radius, is 0.5 meters. Okay. So first of all, if this is the angular speed, what's the frequency? Well, you might remember that the angular frequency is equal to 2 pi times f. So that means that the regular frequency is the angular frequency over 2 pi. So that's equal to 60 radians per second. And remember that the 2 pi has understood on it the units of radians, but we can drop those units whenever we want because radians are dimensionless. But you got to remember that you have to kind of remember that they're there. Radians and cycles are not the same thing. They differ by that factor of 2 pi. So although we will often drop the writing of radians, you got to kind of remember that it's there. Now, when we cancel the radians out, what have we done? We've just converted radians into cycles. So now this is equal to 9.549 cycles per second. And we know that this is just equal to hertz. Rounding this to 2 sig figs looks like about 9.5 hertz. You could write hertz as inverse seconds, 1 over seconds, s to the minus 1. People write it as rev per second or cyc per second. Remember that whenever you see hertz, it is always cycles per second and never radians per second. It would be incorrect to write hertz if it's actually an angular speed or an angular frequency, and vice versa. It would be incorrect to write radians per second if you're talking about a regular frequency. Okay, now that we know the regular frequency, what's the period? Well, period and frequency are simply reciprocals of each other. So keeping an extra sig fig here, hertz is cycles per second, so when I take the reciprocal of that, I'm going to get seconds per cycle. So period, again, just has units of time, although what's understood is time per cycle or time per revolution. Rounding to 2 sig figs, it looks like this would be about 0.10. All right, so when this washing machine is spinning at full speed, it looks like it takes 1/10 of a second to complete one rotation, one full rotation, or put another way, it completes 9.5 rotations every second. That's what hertz is, cycles per second. So 9.5 revolutions per second. All right, moving on to uniform circular motion. Let's imagine a little piece of clothing that is flattened against the wall and that is tracing out uniform circular motion with a radius of 0.5 meters. So in other words, right on the inside edge of the wall. What's the linear speed of that piece of clothing? Well, we know that the linear speed of something in uniform circular motion is 2 pi r over t. We now know the period. We were given the radius. So let's use that equation. Okay. When I calculate that, it turns out I get exactly 30 meters per second exact. So 2 sig figs. Now, there's more than one way to do this. You might remember that V was also equal to omega times R. Okay? So in that case, we could use that. And so this is an alternative solution. And we should get the exact same answer if we've done everything correctly. 60 radians per second times 0.5 meters. That's exactly 30 meters per second. Again, remember, radians are dimensionless, so we can drop them whenever we want, or we can conjure them back out of nothing whenever we want. And the same is true for cycles and revolutions. So radians times meters divided by seconds is just meters divided by seconds, because the radians can just go away. Now we're asked, what's the acceleration of that piece of clothing as it traces out that circular motion? So we know that anything that's executing UCM is going to have a constant acceleration equal to v squared over r. Or, if we want, we can instead use omega squared times r. Either one should give us the exact same answer if we've done everything correctly. All right. So the acceleration of a piece of clothing on the inside edge of this washing machine as it spins is massive. This is 1,800 meters per second. So that's a lot. In fact, we can try and calculate what that is in G's, which is what the problem actually asks for. So 1 G is 9.8 meters per second squared. So converting our meters per second squared into G's, we get about 183.7 G's. And looks like it's a 2 sig fig problem, so I guess we'll chop that back down to 2 sig figs. So no matter which formula we use, we should be able to arrive at that same answer, 180 G's. So that's why the clothing gets all the water squeezed out of it. Imagine it's like imagine it being on the surface of a planet whose gravity is 180 times stronger than that of Earth. It would just crush it. It would just squeeze it flat. Now, if the piece of clothing is, let's say, a pair of jeans that has a mass of 0.8 kilograms, what's the net force acting on these jeans that's required to accelerate them with that acceleration? Well, the net radial force acting on the jeans has to be equal to the mass of the jeans times the radial acceleration of the jeans. Okay? So make sure that we use our MKS units, not Gs, right, which are not MKS units. Now, kilograms times meters per second squared should give me newtons. And that comes out to 1440 newtons. Rounding to 2 sig figs, that'd be 1.4 kilonewtons. If we wanted to, we could have used mass times velocity squared over r, mv squared over r, and that would give us the same answer. Now, let's think about this for just a moment. Which physical forces are responsible for creating this sort of this net force in the radial direction? So if I think about a piece of clothing inside this drum, inside the washer. So here's my spin axis as the washer spins. And here's a piece of clothing on the inside edge. Then as the washer spins, which forces acting on this clothing point toward the center of rotation? Because remember, this is the radial direction, right? This is the radius of curvature of the circular motion. So I can think about the different forces acting on this pair of jeans right here, this wet piece of clothing. There's weight, which in this case is not acting toward the center of rotation, right? It's acting perpendicular to that. There's probably friction then, static friction. If this were perfectly slick on the surface, then the jeans would just slide down. So maybe there's static friction that holds them in place. So it's probably a friction force, but friction force, it turns out, is also only ever parallel to the surface of contact. So that doesn't help in this case. There is a force that's always perpendicular to the surface of contact, and that's the normal force. In this case, the normal force will actually be huge compared to those other two much smaller forces. And the normal force, in fact, does act in the radial direction and in the correct sense of the radial direction as well, right? So it's not outward, it's inward, toward the axis of rotation. And that's exactly right. So it turns out it's the normal force from the wall of the drum that is primarily responsible for providing all of the centripetal or radial force in this case. The weight of the jeans and any friction that are holding the jeans in place on the wall are both perpendicular to the radial direction. So they provide no centripetal force at all, and they're not doing anything to help keep those jeans moving in a circle. Okay, so I'm going to leave questions 3, 4, and 5 to you, as these don't require any calculation. It's question 5 is similar to what we've just been talking about just now, which is when you think about a car going on a circular curve on a flat road or on a banked road, what are the physical forces that together help to push toward the axis of rotation and keep the car moving in a circle? So this is a side view. Keep that in mind, okay? Not a top view. So the car is traveling into the page. Also, for problem 4, what happens if an object is traveling in uniform circular motion and then suddenly all the net forces acting on it disappear? So suppose you're spinning something at the end of a rope and the rope suddenly snaps. Ignoring gravity, ignoring weight, pretending you're spinning this object in outer space, then far from any planet, what direction will the object then travel? And then finally, question 3 is just a review of the directions of the vectors that we've been talking about, the vector quantities that we've been talking about in the lecture. So I'll just leave that to you as a little review quiz to remind you of those quantities. So I'm going to switch back to the slideshow, and that concludes the lecture. Just as a reminder, try those remaining tutorial problems for extra practice, or go to the online homework and complete the first portion of it, which are problems on circular motion. The second portion of it, of that same assignment, is problems on gravitation.